at Berkeley, mainly focusing on engineering entanglement between qubits in this superconducting platform. Yeah, but I think kind of a fun first place to start, because we're all here discussing actually doing computation with quantum dits, would actually be to look a little bit into history and see, because there is actually a history of using classical dits for doing regular computation, and I think it's at least some fun trivia. Okay, so when I was going back and trying to look into this history, the first place I actually saw classical dits pop up for accomplishing some task of interest was in rural England in the 20th century. There was this gentleman by the name of Thomas Fowler who had to calculate taxes in a parish with an extremely complicated currency system. So yeah, so currencies had to be, the taxes had to be calculated in farthings, which were worth 1/960th of a pound, 1/48th of a shilling, or a quarter of a penny, before then being converted back to pounds, shillings, and pence. And he actually found that a really natural way to do this was to build this wooden calculating machine based off of a balanced ternary logic. And then actually through the mid part of the 20th century, in the early period of classical computing, with digital computers, the Soviet Union actually had a big effort to develop a ternary-based classical system for supporting a bunch of their scientific projects at the time. And they actually built, I think, 50 total of these machines called the Sedans, based off of again, a balanced ternary logic. And they used, at this time, magnetic cores and diodes to achieve their computation. And I think looking to the future, maybe there's still actually some hope for classical trits and dits, because we're coming up against the very limits of Moore's law based off of the sort of constraints of miniaturizing circuit components. And so Samsung has already actually been exploring developing ternary CMOS junctions as one way to continue to expand computational power in devices. Okay, and then for us at Berkeley, how do we start thinking about quantum dits? Well, the first actual reason we decided to look into at least qtrits was based off of an idea from Norman Yao and Benny Yoshida around this black hole information paradox. So there's this sort of crisis in modern physics between the unitarity of quantum mechanics and the predicted black holes in general relativity, and what happens to our quantum state if it falls into a black hole. So it turns out that maybe there's some hope for this. Decoding is still possible if you have some quantum resource entangled with your state as it falls into a black hole. And then there's this analogy, at least, between quantum information scrambling and these black holes. And so there was the idea that maybe quantum computing can help us study some of this physics. And the reason why qubits were interesting for us at first, back in 2018 when we were proposed this idea, was because the smallest or most compact physical system where you can actually probe fully scrambling behavior is actually a 2-qubit system. So they actually went and performed this experiment back in 2020. And we're able to demonstrate quantum information scrambling around teleportation protocols. Okay, so just sort of map out a little more of the landscape of superconducting circuits and qubits. In the world of superconducting circuits, we kind of have a few basic building blocks to play with. We have capacitors, we have wires, we have inductors, and we have Josephson junctions, which give us our nonlinearity. And from that, we can build up our own sort of Mendelev's table of elements that are all of these circuits with different sort of energy level structures. So on one end, we have oscillators, which have an infinite dimensional Hilbert space and basically no anharmonicity. And then we have these small anharmonic Kerr nonlinear oscillators, the transmon, which I'm going to talk a lot more about, which is sort of in this middle ground of anharmonicity, and then fluxonium, where we try to engineer a very large gap and have really an isolated 2-level system. This sort of lays out part of the landscape on one axis. Another axis you might think about is the actual qubit dimension. How many levels can we effectively encode in each of these circuits? That's what we're interested in here at this conference. And then another axis might be, how many of these qubits can we actually couple together and effectively work with? And so for my talk today, I'm going to be focusing in this sort of region, which is where we've been focusing at Berkeley, which is encoding, say, 2 to 4 levels in our circuits, and then trying to just build out the techniques to start scaling up these qubit systems right now in the range of only a few qubits, but with an eye towards actually scaling up these systems. And so yeah, the goal is then to develop both single and 2-qubit gates that are efficient, that are entangling, ideally fully entangling if we can figure out how to do it, and scalable, so flexible to implement on the hardware. But also, I would like to just point out that in the world of superconducting circuits, just this year, there's been some really exciting developments from both the Cornell team and the Rochester team, where they've been able to, in the single qubit level, push up this qubit dimension on this other axis to like 8 to 10 levels, and actually demonstrate universal control in these systems. Okay, so we've already heard a bunch of reasons at this conference for why qudits are interesting. So at Berkeley, some of the reasons we think about why we are actually excited about working with qudits. So I guess this large Hilbert space argument has already been made. But one can still think about for a sort of naive problem like random circuit sampling, probing the regime of quantum advantage with, say, half as many Q-quarts as required qubits. But maybe of more interest in the near term, and to physicists like us, are problems around quantum simulation. So there's a lot of quantum simulations that naturally map to qudit architectures, such as probing higher spin physics, fast scrambling dynamics I talked about, lattice gauge theories, which we've already heard very nice talks about, and also things like collective neutrino oscillations. And then obviously, we also just heard a great talk about how qudits can be used for error correction. This can also be interesting for maybe like transmon-based codes, because there's reasonable theoretical expectation of higher noise thresholds if we can actually use qudits to encode logical qubits or logical qudits. But yes, with all of this, it's great. There's additional operational complexity for sure. So we want to focus specifically on how we can improve our circuit design, our control, and our fabrication. And mostly today, I'll be discussing our work on control. OK, so just to first start out, before we get into entanglement, with just what are the qudits in our lab, and how do we actually control them at least a single qudit level. So for us, we use the transmon. We already got a little introduction to the transmon before, but I kind of just want to recast it as a multi-level system. So the transmon is essentially this, or nearly this Kerr nonlinear oscillator. So its enharmonicity is basically determined by how large we set the shunt capacitance in our circuit. And by choosing sort of a suitable choice for the EJ and EC in our circuit, we can actually robustly encode in many levels of this system. And I think you can think about it roughly as like a virtual atom with many bound states. So part of the story of why it's even interesting to think about using these transmons as a qudit-based architecture has been this sort of explosion in coherence in superconducting circuits over the last 20 years, which still is steadily improving. And already this plot is out of date. But we've seen a 6 to 7 orders of magnitude increase in superconducting lifetimes for qubits over the last, say, 20 years. And then part of the story for us at Berkeley has been noticing that as these coherences have steadily increased, the coherence of the higher levels has also come as well. So this is from a recent paper from our group, where you can see the sort of characteristic single photon lifetimes in the 1-2 subspace of our qtrit. So the higher level subspace has already reached lifetimes that were state of the art for qubits only a few years ago, which really leads us to think that these are computational resources that are worth exploring. OK, so how do we do basic readout at, say, the single shot level of these qudit devices? Basically, we just couple this transmon circuit to a linear element, which is just an oscillator. And this basically realizes effectively a generalized Jaynes-Cumming Hamiltonian, where the sort of amplitude and phase response of this linear oscillator on our chip is just dispersively shifted based off of whatever state our qudit is in. So here we just show an experiment where we prepare each of the cardinal states of our qudit, where we encode up to 4 levels in one of our transmons, and then probe the readout response. And then by choosing an appropriate frequency to probe the qudit at, we can perform a heterodyne readout experiment with an integrated quantum limited amplifier. And we can actually, basically, in the IQ plane of our readout signal, fully distinguish all 4 of our qudit states in a single shot basis, where we generally just use a Gaussian mixture model for discriminating the states. And then here I show basically the characteristic fidelities of our readout in one of these devices. And also what's nice about this is that we can multiplex the readout of all of these qudits in a single step and read them out in a single shot fashion on this 8 qudit device here. OK, so how do we do gates at the level of single qudits? This is basically just by driving single photon Rabi oscillations in each of the 2-level subspaces that are connected of our qudit. So these I+1 levels. And we basically just turn on tones that are resonant there We show the results of these Rabi oscillations here. You can see sort of the characteristic bosonic enhancement. Our lifetimes do fall off as we go up the ladder, but this will be part of the story for today's talk. Even though we lose a little bit in lifetime, we can actually go faster. So we see some trade-off because our matrix elements are larger, but the trade-off is not too bad. So how do we build up from these local single photon Rabi oscillations to arbitrary control? We basically just compile with these local rotations. So you can see if we're doing an arbitrary Qtrit gate for SU3, we have sort of these 3 blocks of SU2 rotations in each of the qubit subspaces of our Qtrit. And for a Q-quart, we have to do a little bit more of these rotations. But then we can actually go and benchmark doing arbitrary Clifford gates where we encode 2, 3, and 4 levels in our transmon. And the results of one of these randomized benchmarking experiments is here. So obviously, the fidelity does fall off as we encode more levels. But this is basically just a product of the fact that we have to actually compile more gates. But actually, if we look at the native gate fidelity in these experiments, the native gate fidelities are above 3 nines for both the 2 and 3 level encoding. And for the 4 level encoding is just a little bit below 3 nines. So we don't see a large trade-off in actual native gate fidelity. And there's probably some techniques we can actually introduce to still improve this. OK, so that sort of covers the single qudit work, just to give a flavor for what the actual qudits are in our group. So now the sort of meat of the talk is how are we actually able to couple these systems together and entangle them. So like I said before, the sort of chip we're using as a testing ground for a lot of these ideas is this chip of 8 qudits coupled in a ring, where our qudits are all fixed frequency for sort of added robustness and have fixed coupling as well. And so in these systems, there's a few ways, at least known, to engineer entanglement. So there's the sort of cross-resonance effect, which is used by, say, IBM. Our group has developed this technique called the differential AC Stark physics, which we can use to engineer basically a native ZZ-like interaction to get 2 qubit gates, 2 qubit CZ gates. And we've been able to also apply and generalize this physics to do fully entangling 2 Qtrit gates. So yeah, so the idea of this, this differential AC Stark physics is that if we turn on simultaneous off-resonant drives on both of our qubits, then this realizes an effective Hamiltonian that has some local unconditional Stark shift terms, but critically a ZZ-like conditional Stark shift term that is actually tunable with the parameters of the drive. And then this effective Hamiltonian with the ZZ term is basically the generator of control phase gates. So we can use this to realize arbitrary control phase gates in our system. And we've been able to realize 2 qubit CZ gates with the fidelity of around 99.5% across on our devices using this approach. So how do we actually generalize this physics to understand creating a fully entangling interaction for qudits? So if we start in just the second quantization picture with our system of 2 qudits coupled together by just some fixed coupling J, where we approximate the transmon here as a Duffing oscillator, then if we go into the doubly rotating frame of our qudit, where we get rid of all non-entangling phases, basically, then we have, again, this sort of ZZ-like Hamiltonian. Only now, because we're dealing with a larger and more complex Hilbert space, we actually have to address many more entangling phases. So in our system, if we just deal with Qtrits, then we have now 4 entangling phases, whereas this alpha 1,1 term is just, again, the 2 qubit ZZ term. So this tells us basically how to engineer a sort of static entangling interaction on our system, but it doesn't actually give us an engineerable entanglement. So the way we do this is by, again, introducing these simultaneous off-resonant drives. And then as long as we're truly off-resonant with everything and still working adiabatically, then we should be able to map again to an effective Hamiltonian, where we still have this Kerr coupling Hamiltonian, only now the alpha sub ij that control these entangling phases should be tunable with the different parameters of our Stark drives, namely the frequency, the amplitude, and the relative phase of our Stark drives. OK, so we want to characterize this physics. We basically put both of our qudits in a full superposition. We turn on the Stark drive, and then we perform tomography to measure all the phases. So on the top right here, we have the results of one of these experiments. We see our model predicts a linear accumulation of entangling phase. We see very nice agreement to this model. This doesn't necessarily tell us that this entanglement is actually being engineered by the drive. So to do that, we need to vary a lot of parameters of the drive and make sure that things match our effective model. So here on the bottom left is the results of an experiment where we turn on the Stark drive and we vary the relative phase of the drive. And when we do this, we expect from our Hamiltonian model that sort of all the alpha sub ij terms should have the sinusoidal behavior, and we see very nice agreement. Similarly, our model predicts that we should have an omega squared behavior for the alpha sub ij terms based off of the amplitude of the drives. And again, we see pretty nice agreement. The frequency-dependent behavior is a little harder to capture just due to some experimental non-idealities that have to do with like the transfer function of the chip or like the distortion of the microwave field given all of our filtering. But we still can get reasonable agreement to an ab initio master equation simulation. And I think like the main takeaways is we have this interaction that we can tune to entangle the full 2-qubit Hilbert space of our device. And then compared to a static interaction, we can engineer an increase, a sizable increase in the actual strength of this entangling interaction. So we want to use this to generate 2-qubit gates. So how do we actually think about what are the 2-qubit gates of interest? What are the unitaries that we should actually target? We already got a nice introduction in the last talk to generalizing the Pallies to this Weyl-Heisenberg group. We have our shift and our phase operator. And then we can generate this sort of whole Weyl-Heisenberg group with linear combinations of just x and z, such that they span SUD. And this allows us to just readily generalize the notion of 2-qubit gates to the 2-qubit space. So we can generalize the idea of a control z gate by just taking some control state n and applying a qudit z to the n to its target. This is locally equivalent to a C-sum gate, which is just a generalization of the 2-qubit C-naught gate just via conjugation with Hadamard's. And as we think about the fidelity of these gates, I think to think about what fair metrics are, it's actually a little bit difficult to actually come up with fair metrics, but we should think about even at the level of a 2-qubit gate, this is sort of a larger Hilbert space than even a 3-qubit Toffoli gate. So the fidelities might not be competitive still with 2-qubit gates, but we're entangling on a large Hilbert space. Okay, so by tuning these alpha sub ij terms with our Stark drives, we can engineer and tailor our entangling phases to realize these like 2-qubit CZ unitary and also CZ dagger, also using a little bit of dynamical decoupling to relax some of the conditions for realizing this with the following pulse scheme. And then we went ahead and benchmarked this gate using some of the techniques in the randomized benchmarking toolbox, both cycle benchmarking and cross-entropy benchmarking. And this also allowed us to extract a pretty good error budget for our ability to tune up this gate. So with cycle benchmarking, we were able to extract a 2q-trit CZ fidelity of about 97.5%. And then we also used XEB to get an extra validation of this fidelity. We also can extract from XEB roughly the purity limit of our gate, and we see that we have some control error still in our system. And for our current gate speed, should still be able to push this fidelity above 98%. And then as we think about why it's actually powerful to have a fully entangling 2-qubit unitary, if we think about basically synthesizing other unitaries from this gate in terms of how many two-body operators we need, then if we want to use the CZ gate to, say, compile any Clifford gate, we can do essentially any 2-qubit Clifford gate with only 2 of these gates. And then when you go to hard random gates, you can do it with only about 6, whereas only subspace entangling gates require a lot larger depth of these circuits to synthesize these unitaries. Okay, so that's how we've been able to do these fully entangling 2-qubit gates. Another thing of interest in our group has been how can we actually engineer exchange interactions on a device that's fully fixed, which is not something that had been typically understood. And the approach we've had to doing this is with Floquet engineering. So why are these exchange interactions interesting, even at the level of 2 qubits? These Heisenberg interactions serve as the primitive of a lot of physics of interest, from analog quantum simulation to gate-based algorithms. Typically in superconducting devices, to engineer these XY-like interactions or this Heisenberg model, one has to introduce flux-tunable elements. And this has been done very successfully using, say, parametric couplers, or tunable qubits, or even systems where you have both parametric couplers and tunable qubits, so fully flux-tunable device. But there is some drawback, and that's that we're introducing a lot of 1/f flux noise to our device. If we can tune our devices with flux, so can the environment. So there is one question that naturally arises, and that's, can we tune these qubits without flux? So the way we've devised to do this is just with this Floquet engineering. So the idea is if we have a time-dependent Hamiltonian, but our time dependence is periodic, then we can sort of exploit that structure to map our Schrodinger equation to this Floquet equation, where now our sort of, we can think about it basically like a time-independent Hamiltonian, only now we don't actually have the associated eigenenergies, but these quasi-energies, which can now be tunable with the parameters of our start drive. So that is basically how we can engineer a tunable eigenenergy into our system just via microwave. So how do we actually synthesize these flow K qubits? We start in our bare state, maybe some mixture of states. We adiabatically map ourselves to a place where we can turn on Heisenberg interactions, where we can bring these quasi-energies, these flow K quasi-energies into resonance. And then we adiabatically map ourselves out of this space to then perform readout with the techniques we've already shown. And we've also used some shortcuts to adiabaticity methods to speed up as much as possible this ramp between our bare and flow K states. Okay, so a first experiment we might want to do to verify that we actually can engineer these XY Heisenberg interactions is just trying to take two qubits, put them onto resonance for their quasi-energies, and then show this XY I-swap-like flopping. So here's a characteristic chevron where we've red detuned one of our qubits, blue detuned the other qubits, swept them through resonance, and then if we look at a cutout, we see very coherent 1, 0, 0, 1 swapping of our two qubit states. But then to actually achieve full control via this flow K engineering over the Heisenberg model, we also need to be able to engineer our anisotropy. So we can add an extra drive that uses to do basically the spin-spin interaction, and we show that we can simultaneously tune the XY and the spin-spin interaction to do a fully programmable XXZ model on our qubits via this flow K engineering. So one way we can actually benchmark our ability to perform these measurements and map between our flow K qubits and our bare qubits, and something that we're very comfortable in the lab is to just tune up 2 qubit gates and benchmark them. And there's actually many 2 qubit gates where the primitive of those gates is actually the Heisenberg model with various different terms. So we have, say, the I-swap gate, which is just our XX plus YY. We have our CZ gate, which is just this Ising spin-spin term. And then we also have the full swap gate, which has an equal contribution of XX, YY, and ZZ. So this really demonstrates that we can tune up all these gates, that we have full control via this flow K engineering over our full XXZ Heisenberg model. And we actually went and benchmarked all of these gates using this flow K engineering, finding reasonable fidelity for all of them. Okay, and then the sort of second piece of this flow K engineering, where we kind of want to complete the toolkit for these interactions in our device, which typically isn't thought of as having the ability to perform these more complicated interactions, is to engineer XX minus YY-like interactions via 2-photon entanglement. So the basic idea here is to use essentially a 2-body Raman process. So we want to drive some parity-forbidden transition, between some intermediate state. Here we just drive between 2 intermediate states. And if we can do this in our qudit, we should be able to realize KL to K plus 1, L plus 1, XX minus YY-like oscillations via this physics, where again, we have to perform this flow K mapping where we adiabatically map ourselves to the space where this transition is actually achieved. And again, there's a few nice things about this. First of all, the anisotropy is again adjustable via this extra spin-spin knob. And really critically for a system like ours where we have fixed frequency coupling and fixed frequency qubits, the actual resonance condition of these XX minus YY-like interactions can be totally tuned, which allows us to avoid, say, frequency collisions with unwanted transitions on the chip. Okay, so again, I show here just like the 2-photon Rabi oscillations between 0, 0, and 1, 1 using these Raman transitions. We see the nice chevron-like behavior. As we go up, though, when we look at the, say, 1, 1, 2, 2 flopping, we actually see an example of a frequency collision. So we notice that the excitation preserving your XX plus YY-like transition for 1, 1 swapping with 0, 2 happens to be quite close to the 1, 1, 2, 2 in this case. But because, like I said, we have with this flow K engineering the ability to detune these things in the dress frame, we can actually move these 2 transitions far enough away from each other such that when we look at the 1, 1, 2, 2 flopping, we see that it's highly coherent and has sort of no deleterious effects from this nearby transition. And then we actually studied these entangling interactions up to d equals 4. I think this is the first attempt to actually entangle qudits up to d equals 4 on a superconducting platform. And we're able to see that, again, the resonance condition can be tuned over tens of megahertz for all of these transitions for our 2 qudit system. And we can actually turn on interaction rates in, let's say, the 2233 subspace of our qudit that are so many times faster than in the just 0011 state. So again, yeah, we take a bit of a hit in coherence, but we can go a lot faster. So one of the first ways we thought to just benchmark these two-photon interactions was just create Bell states and then look at the state fidelity with state tomography. So if we just turn on this 0011 swapping, we can realize in a single step where we look at like half a Rabi cycle, a 2-qubit Bell state. We can turn on the swapping between 0011 and 1122 to realize a 2-qubit Bell state. And similarly, if we turn it on with 2233 as well, we can realize a full Q-quart Bell state, or so this D equals 4 entangled state. And if we look at the state fidelity of these Bell states as we go up the ladder, we see that the fall off in fidelity once we get to D equals 4 is about 94-ish%. But if we look at the purified density matrix, where we just numerically purify the density matrix to find the nearest idempotent density matrix, we see that we actually have introduced very little control error. The fidelity is pretty good. We're basically limited by bare decoherence. OK, so we wanted to just demonstrate that if we imbue these two-photon interactions, if we can actually engineer them on our chip, then we can fully programmably distribute qudit entanglement across the chip. So if we start in, say, a 2-qubit Bell state here between one pair on one side of the chip, where we just show the parities, then I can distribute this entanglement anywhere via these two-photon swaps into non-local Bell states. Or I can generate GHZ states very efficiently, also from this beginning entangled state. And then because we're a superconducting platform, we have a very fast clock cycle, which means we can do crazy things like actually measure the full 4-qubit state tomography. So we can actually go and measure a 4-qubit GHZ state and verify that we can pass an entanglement witness protocol and really do have a fully entangled 4-qubit state on our chip just via these two-photon interactions. And then as like a final, sort of a final demonstration of sort of the power of using qudits on your device, we've talked a lot about how we can use them for doing qudit-based things, but they also can really help us for doing qubit-based things. So if we can use the higher levels of our system basically as an on-chip ancilla without requiring additional transmons, then we can, with much fewer number of two-body interactions, really effectively compile n-body gates, which is really nice in a system like the transmon where we have limited connectivity in our system. So we use this two-photon swapping in these higher levels like ancillas to compile 3- and 4-qubit gates. And we were able to benchmark 3- and 4-qubit CCZ and CCCZ gates with fidelities of about 96% and 90% fidelity, respectively. And then as we look towards the future, and why this is sort of interesting, you get sort of a large asymptotic advantage in the number of two-body gates if you can even have access to a single extra level in your system for compiling these big n-body gates. OK, so just to summarize the talk so far, we've really focused on functionality, creating some tools to scale up qudit-based computation and superconducting circuits. We've been able to engineer this fully entangling 2-qubit CZ gate. We've also used this flow K engineering to build out the toolbox for resonant-like interactions in our system. And then as we look towards the future, we really want to improve the fidelity and performance of all of these underlying operations. So we're really pushing hard on test devices to improve our coherence. And we've also been integrating parametric couplers and are interested in studying them for 2-qubit gates because we've already been able to achieve much faster 2-qubit gates using them. And with that, I just want to thank everyone back at Berkeley and open the floor for questions.